Swayam Prabha. Digital India. Educated India.
So, any question on parallel stochastic gradient descent using mini batches? What is the problem with parallel stochastic gradient descent on mini batches? What is the problem? So, the problem is, you see, you are doing too many distributed iterations, right? So, you are just computing. So, typically you would like to do maybe 1,000 computations on one machine and then maybe share one data point, right? So, if you compute, so if you, let's say, if you have a network, right, and if you are doing, so what is your typical transfer rate of data between two computers which are directly connected via, let's say, Ethernet? It is like, let's say 10 Mbps or 100, even 100 Mbps, right? So, 100 bits, 100 million bits it can send per second, right? But how many bits can the CPU compute on per second? Typically 2 gigahertz or something, and each time it can compute on at least 64 bits, okay? So, something like 128 trillion, right? Giga means 10 to the power 9, right? So, trillion bits, okay? So, you can do computation within the machine on roughly 3 to 4 orders of magnitude bits of data more than you can send, okay? So, it is very wasteful when you do computation on, you compute the gradient, okay? So, doing computing, so you are computing, let's say, the gradient with 100 parameters, okay? So, 100 bits, or let's say 100 into 64 bits you are computing, okay? You are, in order to compute, you will need maybe maybe 100 more operations per bit, okay? So, you are still 2 to 3 to the power 2 to 3 orders of magnitude lower than utilizing your CPU. So, you will see that your CPU utilization is at 0%, but your network utilization becomes 100%. Is it clear? So, even a very optimized implementation of distributed stochastic gradient descent has the problem of what is called the communication bottleneck, okay? So, you are sending too much data around in order to do the updates, okay? And you are not doing enough computation. So, your CPUs are lying idle, okay? So, you would like to change that, okay? And the way to change that is using what is called a ADMM. So, I will skip this part. So, this is the graph I wanted to show you. So, this is a typical graph that you get when you do a stochastic gradient descent, okay? Okay. Now, I have told all this. So, now for this we discuss what is called the ADMM. So, what is an ADMM? ADMM is a meta optimization algorithm, okay? What it does is it takes a distributed data set, okay, and it takes what is called a decomposable loss, okay. So, what is a decomposable loss? Decomposable loss is a loss which can be expressed as the sum of losses over, let's say, data in different machines, okay, and it can optimize this entire decomposable loss, so sum of all these losses, by the scheme where it first optimizes the loss locally and then it shares some information, okay, and it keeps doing this iteratively until it converges, So, I am going to tell you how this works. Okay. So, okay. So in order to do this, so I will tell you the solution upfront. Okay. So, before even going into this thing. So, how will I do this? I will do this in a very simple way. I will so let's say I want to minimize my f of x, which is f1 of x plus f2 of x plus fn of x. Okay. What I will do is I will write this as f1 of x1 plus f2 of x2 plus fn of xn. Can I do this? So, I want to minimize this with respect to x. Okay. Instead, I will minimize this function with respect to x1, x2 till xn. Okay. Will this work?
There is some kind of strong assumption we are making.
There is some strong assumption. So, what is that strong assumption? So, you have a feeling that it will not work, right? Very good, actually. Your feeling is correct. So, can anybody tell why it will not work? What might happen? First of all, if I do this way, what is the advantage? Can I say that solution to this problem is same as minimum over x1, f1 of x1 plus minimum over x2 plus, can I say this? Why? Because the other things are not dependent. Okay. What is the problem? Is this clear? This logic is clear? Okay. I am just telling without going into all the details of maths. Okay. Problem is that this may come up with some x1 star, this minimization may come up with some x2 star, and this may come up with some xn star, and these need not be equal. Okay. But you have to finally report one x. So, which x will you report? Clear? That is the problem. Okay. What is the solution to the problem? So, in addition to writing this, you also write, so you know about constraint optimization problems, right? So, you add this constraint x1 is equal to x2 is equal to xn. If you add this constraint, okay, you are done. Okay. In fact, I will add a different constraint. I will add a constraint xi is equal to some z for all I.
How can we make sure that it will be same about some functions?
Huh?
How can we make sure that these x's will be same?
No. I am right now. I have not talked about algorithms. I am only talking about the formulation. Right. So, for example, SVM you write a formulation, right. So, when you write a formulation, you do not talk about algorithm. You are just talking about the problem here. Okay. So, I am just trying to come up with the right problem, then I will tell you the solution. Clear? So, I am trying to come up with a problem which is same as this original problem that we wrote down, okay? Okay? And which is amenable to a distributed solution. And I come up with this problem. So, what is this problem? This problem is simply that you minimize with respect to x1, x2 till xn and z, okay, f1 x1 plus f2 x2 plus all this, okay, subject to xi is equal to z for all I. So, at least now you agree that these two problems are equivalent. I still do not know how I will solve it. Okay? Okay? So, this is the problem I will now look at. Okay? So, let me see how I will look at. So, I will just look at this problem. So, I will look at solutions for equality constraint problems. Okay? Equality constraint problems are problems of this type. Okay? So, you have minimize fx subject to ax equal to b. So, this is like x is equal to b is a special case of this. We are having more linear kind of equalities. Okay? Okay? Now, this is an algorithm for this. So, what is this algorithm doing? This algorithm is also called the dual ascent. Okay? So, all it is doing is it is optimizing the dual the Lagrangian with respect to the primal variable, and then it is doing a gradient descent in the dual. Okay? And you can check that this only works if the Lagrangian is strictly convex. Okay? I will not go into detail of this because we are kind of short on time. Okay? But and this can be also generalized to if you have n functions f1 till fn with n variables with the constant that x1 is equal to x2 is equal to till xn. Okay? So, this is the type of problem that we want to solve, and then we can do dual ascent type algorithm. So, dual ascent type algorithm will minimize each of these L1 till Ln in a distributed manner. Okay? It will get x, okay? And then finally, it will just do this step, this y step with all the y. So, y step is very easy, y step is just something like this. Okay? The problem is it will not work if your Lagrangian is not strictly convex. Okay? So, this is also called dual decomposition. This is the algorithm. Basically, for the ith node, you optimize the dual problem with respect to only the primal variable on that node. Okay? And then on the central node, you just take all these optimal solutions and you just add this. Okay? So, this is a distributed solution for that. Okay? Unfortunately, so that problem of strict convexity is solved if you use what is called an augmented Lagrangian. So, you have probably seen Lagrangian only till this part, right? Have you seen this augmented Lagrangian anywhere in the optimization? Okay. So, you have seen till the first two terms. First two terms say you have the objective function, you have the constraint, and constraints are multiplied by the Lagrange multipliers. Okay. But here we have a second order term on the constraints. So, we are saying that the second order terms of the constraints should not be violated. Okay. So, okay. So this is our augmented Lagrangian. Okay. Now, if there is only one, so this is not a decomposable function, right? There is no x1, x2. Okay, there is only one x. Then you can, your dual ascent with the augmented Lagrangian becomes this. This is also called sometimes the method of multipliers. Okay, same thing, but instead of Lagrangian, now you optimize the augmented Lagrangian with respect to the primal variable, and then, so here there are no variables. If you can see, there is only this rho which is a user supplied constant. Okay, so there are no variables in the second term. So second term is a fixed. It's like how much far away you are from violating how much are you violating the constant. That's all. Okay. So if this is the case, and you solve this, so if you do a gradient descent on the dual, rather gradient ascent on the dual, because dual has to be maximized, okay, with respect to the dual variable, you get the second step. Clear? Okay. You combine these two to get the ADMM. So what is ADMM? So suppose, so I am just showing for simplicity with two variables. Okay, you can generalize it. What ADMM says is that suppose you have a decomposable objective function of this form, fx plus gz. So you have only two computers. On one computer you have the parameter x, on the second computer you have the parameter z. Okay, and your loss is, on first computer your loss is f of x, on second computer your loss is g of z. Okay, and your total loss is f of x plus g of z. Okay, and you are trying to solve this subject to this constant. So think of it something like this, that your a is 1, b is -1 and c is 0. Okay, so you are trying to say that x is equal to z. Okay, something like this. Okay, so if you do this and if you solve this, and then you can write the augmented Lagrangian, and then these are your steps for ADMM. So you first minimize with respect to x. Okay, the augmented Lagrangian with respect to only x. Then you plug in the xk plus 1 and you optimize the augmented Lagrangian with respect to z. Okay, and then you finally optimize this. Okay, and what you can show is that this really converges to the optimal solution. Okay. Okay. So yeah. So by the way, just to understand this, you do understand that so is this a dual ascent on this, or a method of is this a method of multipliers? So the second I have already shown you the method of multipliers algorithm, right? So this is the method of multipliers algorithm. Okay, I showed that this works. Okay, so this is like the dual ascent with the single variable. Okay, with augmented Lagrangian. Okay, is this the method of multipliers with two variables? Yes or no? It is not. Can you tell why it is not? Which term is responsible for this not happening? Second order term. Why? What will not happen because of the second order term? So what will be the method of multipliers update? Can anyone tell? So the method of multipliers update will be this. Okay, so x k plus 1 comma z k plus 1 minimize with respect to x comma z. Okay, L row of x, z and yk, and then your yk plus 1 will be equal to whatever it is, yk plus or minus, I think, minus rho times your ax k plus 1 plus by k plus 1 minus c. And can you see the difference between this algorithm and this algorithm? Okay. So, this algorithm does not decompose. Okay. This does not decompose because this augmented Lagrangian has a second order term. Okay. So, you cannot optimize separately with respect to x and z. Okay. But in this algorithm you are precisely doing that. Okay. So, this requires an extra proof that this indeed converges. It so turns out, so it is not the same as a gradient descent on this thing, but it still does converge. Okay. Okay. So, what must happen? So, what must you check for ADMM to converge? Okay. So, how will you check that ADMM is converging? Okay. And the answer is, you have to check this primal residual. Okay. So every step k you compute this, what is this called, this Rk. Okay. Okay. So, you compute the primal residual. So, if the primal residual is not 0, then what is happening? Your equality constraints are not satisfied, right? Okay. So, for any update, you have never made sure, that in your formulation this should be 0, but every update you have not made sure this happens, right? So, you have to check that this finally goes to 0. Okay. Additionally, you have to check these two dual feasibilities, right? So, if you just take the original problem, you look at the KKT conditions for this problem. Okay. You can see that this is the primal feasibility, then there are two dual feasibility conditions, right? Okay. So, you write down both dual feasibility conditions. So, one of the dual feasibility conditions is automatically satisfied by all the updates, but the other one leads to a dual residual. Okay. So, what you can see is that basically, so these are the convergence results that happens. Okay. So, the primal residual must go to 0. Okay. The dual residual must go to 0. Okay. The objective function must go to p star. Okay. And the dual variable should converge to the actual dual variable. Okay. But it is not a descent method. Okay. So, it may so happen that in a particular iteration your objective function value actually increases, okay, but your dual primal residual decreases. So, you are producing a solution which is more compatible. So, let us say the parameters on the two servers are more equal. So, earlier you are producing a solution where they were less equal. Okay. That equality is measured by the primal residual. Okay. So, the primal residual is high, okay, but the objective function is low. In the next iteration, it may so happen that your primal residual becomes low, okay, but your objective function increases. Okay. So, it is not a descent method, okay, but it can be shown that eventually all this will go to 0. Okay. So, primal residual will go to 0. Okay. So, we will not go into the proof of this. Okay. So, your stopping criterion is when your dual residuals are within a particular limit. Okay. If your all primal and dual residuals are within a limit, you can stop. So, I have a few more things to go over. So, maybe I will. So you can see that you understand the scheme, right? So, you understand that you solve this Lagrangian on each of these machines, okay, and then on the central machine you update what? You update the dual variable, which is the y, right? So this is the scheme. So so there is a small revision, and after revision you can see this is the algorithm. So basically you do this x I k plus 1. So you do on the ith machine you update x, and then you just update the dual variable yi on the central machine, okay, and this is your algorithm, and you can derive it for many. So you can derive it for fully distributed SVM, and then you can do it for some work that we did where you can do a weighted parameter averaging. Again, all this is way of solving this. So yeah, so you can see here. So maybe this will be of this plot will be of importance. So you can see how the primal residual varies as so this DSVM is basically the ADMM, okay. So you can see that the primal residual may go up and down, and then after a while it converges, okay. So the black dotted right is a primal residual for an SVM, okay. Is this clear? So you can think like that, okay. And this is how the accuracy varies with the iterations. But typically what you can see is that the number of iterations required is much smaller. So if you use something like so you see that you get a very good result if you use the accelerated distributed SVM, you get very good result within 50 iterations, whereas you would take 100,000 updates of mini batch SGD for getting good solutions. Okay, so with this I will stop. Any questions? So in summary, you have to do much fewer distributed iterations, and you have to do more iterations on each of the machines because you have to optimize the local objective function in that machine. Okay, so if there are no more questions, you can stop. Thank you.